When we're doing related rates problems, oftentimes problems show up where we need to use similar triangles. And so we're going to do an example of that here in this video and then work from there in class. So one thing to remember about similar triangles from maybe from a geometry class, and this is oftentimes how these are going to appear, is where we have a triangle inside of a triangle. And so a triangle inside of a triangle like this, these will be similar triangles because they have all the same angles, which means that the corresponding sides are going to be proportional. So what this means in this particular case is that like this red side of the big triangle, if I call that maybe A, and the corresponding side of the small triangle are going to be proportional to each other. Let's call that maybe X on the small triangle, is that distance. So, and then the corresponding other side, so maybe if we take the top side here, we'll call that B on the big triangle. And then the corresponding side on the small triangle, maybe that green one. We're going to have a proportion here where we might be able to say that like A over X is B over Y. And so what I'm doing here is that the top numbers are both numbers coming from the big triangle, and the bottom numbers are coming from the small triangle. And the A and the X, those are corresponding sides. They're both the bottom. The B and the Y are corresponding sides. They're both kind of the height here. You could also write this proportion as A over B. So this is a ratio of the big triangle. So the bottom side of the big triangle and then the height of the big triangle. And then we could write a corresponding proportion for the small triangle. So since the A was the bottom of the big triangle, I need the bottom of the small triangle and then the height of the big triangle. So you can write proportions like this for similar triangles. So this is going to be useful for us in giving us relationships between the sides of similar triangles. Okay, so for this particular problem, we have a guy named Bill, and he is 1.7 meters tall, and he's acting in a play. He's walking towards a wall at a rate of 1.3 meters per second, and there's a spotlight on the ground behind him. Okay, so ground over here, the wall is here. Okay, and so the spotlight is projecting a shadow onto the wall. So the way that the shadows always work is we can just draw a triangle over his head, and then we'll have the shadow. So this is his shadow over here. Okay, and let's see. Okay, and so let's see. We know that there's a spotlight on the ground that's 20 meters away from the wall. The spotlight's not moving, so we can go ahead and label that this is always 20 meters. Also, Bill is always 1.7 meters. He's not growing, or yeah, he's not growing during this play. And we want to know at what rate is the length of his shadow changing when he's 5 meters from the wall. Okay, so let's call this side, we'll call it B to correspond with what I had before. So we want to know the rate of change of Bill's shadow, dB dt, when he's 5 meters from the wall. So when this distance is 5, okay? That distance doesn't correspond nicely to a side of the small triangle. So usually what we're going to do here is that we're going to label this side of the triangle. We can call this X like we did before. And then we can kind of make an inference about how long the other side is going to be. Okay. So if he's 5 meters from the wall, that means he'll be 15 meters away from the spotlight. So we're looking for dB dt when X is 15. Okay. And so then let's see, what else do we have here? So we know he's walking towards a wall at a rate of 1.3 meters per second. Would also mean he's moving away from the spotlight at that same rate. So we could say that dx dt is 1.3 meters per second. Okay. And so now we need an equation relating X and B. That's going to be our similar triangle relationship. So we've got our little triangle here. So we can write the ratio for the little triangle. We could say 1.7 over X. And then if we write a ratio for the big triangle, Okay. The 1.7 was the height of the small triangle. So we need the height of the big triangle, which is B. And then the X was the base of the small triangle. So we need the base of the big triangle, which is 20. So we get this relationship relating X and B. It's oftentimes a good idea to simplify this relationship now. So we could go ahead and just cross multiply from here. So if we cross multiply, we get 1.7 times 20, which gives me 34 is equal to X times B. Okay, now we can differentiate this equation because we're trying to figure out how this changes. We're going to take a derivative with respect to time. The derivative of 34 is just 0. And then when I differentiate X times B, I'm going to end up with dx dt times B. I'm doing the product rule here. Plus B stays, oh, nope, X stays the same now. And I take the derivative of B, which is dB dt. Okay. So now let's plug in the things that we know. So we know that X was 15. And we know that dx dt is 1.3. And dB dt is the thing that we're trying to find, which means that before we can finish anything, we're going to need to know what B is. So we need to know what's B when X is 15. And we can do that by using our similar triangle relationship again. We know, let's actually just use this one. We know that 34 has to be equal to X times B. So 34 is 15B at this point in time. So if I do 34 divided by 15, I'm going to get B is 2.26667, or just leave it as 34 over 15. So now let's plug things in here. So we're going to have dx dt. What did I say that was? That's 1.3. B was the 34 over 15. I'm going to leave that precise just so we get a precise number here. And then X was 15. dB dt was the thing we were trying to find. Okay. And so now let's solve this. I'm going to have 1.3 times 34 divided by 15. I subtract that over and then divide by 15. So I'm going to get negative 0.196 meters per second dB dt. That's going to be the rate of change of his shadow when he's 5 meters from the wall. What that's going to be telling us is that the shadow is shrinking at that point in time, that it's getting smaller because the rate of change is negative there.